Any questions from the first hour? The first hour was kind of motivational, give you the big picture. Now we're going to start talking about spectroscopy. And we'll start with the simplest molecule, diatomic molecule. With spectroscopy, we're concerned not about the translational motion of the molecule now, talking about the internal energy. And our simple picture is that we can think about these molecules as being just springs and masses. And that we can think about their rotational motion, their vibrational motion, and their electronic energy that's associated with the positions of the electrons spinning around the outside. The classic way to describe energy is with this diagram here. You'll see over and over again. Energy, vertical, internuclear spacing. So that point right there is the bottom of the potential energy well. That's the equilibrium internuclear spacing of this molecule, diatomic molecule. Independent of whether it's homonuclear, which would mean like N2, or heteronuclear, like CO or NO. So this envelope is just the roll of the charges. And so if you're on this side over here, you might imagine, and maybe you're a long distance away and the two atoms come together, if they're on the line. When they get close enough, they begin to feel each other. And this then is called an attractive potential. It pulls the two atoms into a molecule. If there's no collision while this is taking place over a period of about 10 to the minus 13th seconds, they'll come together, and then it'll go up this side, and the potential energy will equal the initial value, and it'll go back out. So if there's no collision, the two atoms come together. Now they come in very, very slowly. What happens when they go down this well? Conservation of energy. The decrement in potential energy is the gain in kinetic energy. So when they go down here, they've got minimum 0 potential energy, and they're going like crazy. And then they go back out. But if there's a collision somewhere along that 10 to the minus 12, 10 to the minus 13 second process, then that collision, some of the energy is going to be carried away, and the molecule will then not have enough energy to get back out of this well. It's trapped. That's why they talk about the well. But the envelope then is the potential energy associated with the charges. These horizontal lines correspond to the quanta of vibrational or rotational energy. So there's the vibrational energy of V equals 0, V equals 1, V equals 2, V equals 3, anticipating that those V's are the quantum numbers that are quantized numbers. The fine structure you see right here are the closer spacings of the rotational states. And so in general, the molecule will have some amount of rotational energy and some amount of vibrational energy. If the temperatures are low, almost all of the molecules are in V equals 0. Because this spacing might correspond to some sort of a temperature like 2,000 degrees. So if you're halfway cold, unless you're really hot, almost all the molecules live right here with some amount of rotational energy. So we're going to then, if you blow this up here, this is the structure of the rotational energy over here. These are the allowed rotational energy states or levels. I slip and it's really level. I slip and say the word state. Remember, the degeneracy is the number of states that have the same level of energy, magnitude of energy. So here's our simple cartoon. This thing's spinning around and oscillating, and we use this to understand the energy. Remember, we have to understand the energy structure from which we can derive the spectral structure. Energy differences give us the wavelengths of absorption. Now we're going to proceed through 4 sections, so I'm sorry this is kind of rubbed out. So in each lecture I'm going to try to remember to do this. So we'll proceed through 4 sections, talking a little bit about light-matter interactions. Why do molecules absorb light? Why do molecules emit light? And then we'll go to the rigid rotor model. So the simplest model is of we talk about rotation first, because rotation and vibration are independent, and rotation is simple. We talk about rotation first, and the simplest model is called the rigid rotor model. That just says it just rotates, it doesn't stretch. We can relax that a little bit because it's slightly non-rigid, and then we combine vibration and rotation. So that's where we're going to end up for the diatomics here. Any questions? Okay. So light-matter interaction, there's really kind of a simple idea. This is enough. If you imagine a molecule like HCl, that would be a heteronuclear diatomic molecule. That is, the two nuclei are different, heteronuclear, in contrast with homonuclear. H2O is polyatomic and it has a bend. It's more complicated. But think about our HCl, and I should have written mu here. Q is the charge and D is the distance. And so imagine that one end is a little bit positive charge and one end is a little bit negative charge. And what happens when this thing rotates around? If you're looking at it, it looks like there's some oscillation in the electric field. That's how you transmit light. It's an oscillator. But if it's an oscillator, it's an absorber. So if this thing has got an oscillating dipole moment, it's called a permanent electric dipole moment, it's going to absorb light. And it can emit light. So the basic idea is if it's got oscillating dipole, it'll be active in that spectral region. So whether it's emission or absorption, just think about this. So this is basically oscillating dipole moment. Now, if it were homonuclear, would it be oscillating? Homonuclear has the same charge on both ends. You can't tell that it's rotating if you only can see electric dipole. You can't see it. There isn't any. Now we can make it active, but that's a subject to something else. So if it's homonuclear, then it will not have this effect. And therefore, the rotations of the homonuclear molecule will not emit or absorb light. But the heteronuclear one, because it's got a different charge on one end or the other, looks like an oscillating dipole. And we're going to show that in a minute. So now, if it's homonuclear, you might say, well, how do we study it, or how do we even know that it has energy levels? Well, there's always a way. Nature always has a way. And you can, by bringing in electric field associated with a light wave, you can induce polarization. I guess that's why I use P here for polarization. And that's one of those forms is called Raman scattering. Or you can induce what's called Rayleigh scattering. So you can cause transitions in Raman scattering even though it's homonuclear. But that's another effect. That's not the permanent electric dipole moment that I'm talking about. In this Raman case, named after the famous Raman, the famous Indian scientist, you bring in light with a frequency nu, and it hits a molecule, which maybe is initially in state or level n, and that photon goes off with a different frequency, nu sub s. The S stands for Stokes, and the A stands for anti-Stokes. So it comes in at one frequency and it goes out with another. How did that happen? It happens by the Raman effect. Conservation of energy applies. So if this photon goes off with less energy, and the intermediate is called a virtual state, then the molecule has to end up in a higher energy level. So you can convert a molecule from N to M by this effect. You bring in, and it's a weak effect, so you have to bring in lots of energy. Bring in a pulse of light, lots of energy, 10 to the 19th photons. Bring in that light of some frequency, and out goes a photon. You bring in a lot of these photons, and then out will go some of these photons. But conservation of energy applies. You're converting a molecule from N to M. That's called Stokes. And that means that the wavelength is different, and so if you send in light of a certain color, the signal that comes out will be shifted, and you can see it. You can differentiate it. And that's how you find it. But there's also the anti-Stokes, and so you can start with N and end up at M. N and end up at M, which means now the emitted photon has more energy, so therefore the scattered photon has to be, I said that backwards, it goes off bigger. So there's two effects. We had a question about branches. Well, similarly, you have Stokes and anti-Stokes Raman shifts. One goes off with an energy that is changed in one direction, one goes off in a direction that's increased. That's called the Raman effect. That applies even for a homonuclear molecule that does not have this permanent electric dipole moment that you can see when it's rotating or vibrating. So either way, there's always a way to, now if you measure this wavelength, and you measure the change in wavelength, you've measured the energy of the difference between the states that are involved. And if you know the quantum rules, you've just measured the energy, you've measured something fundamental about that molecule. Turns out that the quantum rule is a little different. It may be for this, these to change to quantum number change by 2 as subtlety. The fact is you've measured by measuring the wavelength, you measure the frequency, you measure the change in energy of the state and build up some understanding of the molecule. So mostly we're going to talk about absorption and fluorescence, where we talk about their molecules having a permanent electric dipole moment, and that's the interaction that we talk about. It's slightly different than that for rotation, for vibration, but I'll get to that later. Remember, it's line positions, line strengths, and line shapes. You have to master them one by one. We need the positions of the lines to recognize the spectrum or to anticipate where a line will be. We need to understand the strengths in order to interpret the signal in terms of something we want to know, like the temperature or the number density. And we need to take advantage of the shapes because it may affect the actual detailed nature of our signal, and we might want to use that to advantage to measure, say, velocity or temperature or pressure. We'll learn about this. We'll talk about line positions. So the line position is determined by the difference between the energy levels. The energy levels comes to us from quantum mechanics. I've already drawn you the picture here. We think of the energy as being a combination of 3 types: electronic, vibrational, rotational. So if you were to start right here, suddenly I could somehow create a molecule right there, boom. What would happen? That would mean it had that amount of vibrational energy, and it's going to be oscillating back and forth. So it's going to go down, it's just going to go back and forth. It's going to go from here to here, but the way it goes is down this way. So it's exchanging potential and kinetic energy. And this would be independent of the rotational energy states. So now this is my little cartoon, or I should say it's my student's cartoon, but I'll take credit for it. Typical professor. Okay. So this is that mu is a more correct symbol for the dipole moment, which is a vector quantity, but it's the summation of the charges and the spacings. So you imagine this thing's rotating about its center of mass. One end's a little bit positive, one end's a little bit negative. So every time it goes around, you can see that the dipole moment, being a vector quantity, is down, up, down, up. There's an associated electric field, and I could plot this versus time so it looks like a sine wave. So that looks like a little oscillating transmitter. So a classical picture is oscillating away, and then spontaneously, once in a while, it's going to emit a photon. But that says that it would also absorb a photon. So this permanent electric dipole moment is the kind of the inherent thing that you need to think about in order to have absorption or emission of light. Now, by the way, these rotational energies are such that the energy differences are such that that this occurs in the microwave region of the spectrum. So the waves are like millimeter waves. Spacing of rotational states is closer than the spacing of the vibrational states. So the spacing between the rotational states that are coupled occurs at long wavelengths, microwaves, millimeter waves. The vibrational spacings are shorter. They're in the infrared, low vibrational transitions. They tend to be, we talk about them in nanometers, it'd be, say, 2,000 nanometers, 2 microns. So are all molecules microwave active? No. If this is homonuclear, you wouldn't see this. You wouldn't be able to see any oscillating dipole. And so an example would be hydrogen, chlorine, or CO2. CO2 is a symmetric linear molecule. It's a stick. When it rotates around, you can't see this in the oscillating electric field. So that rotational motion of CO2 would be microwave inactive. So again, if they're microwave inactive, they will be Raman active. So there's always a way to observe the behavior of the molecule, but not necessarily in absorption or fluorescence. Rotations in the microwave region. Vibration is in the infrared region. Rotation means we're going to change J. What's J? J is the symbol for the quantum number for rotation. So for a diatomic molecule, J is the rotational quantum number. For a diatomic molecule, V is the vibrational quantum number. Diatomic molecule is only one vibrational mode. You only need one quantum number. If it were CO2, linear molecule, there are 4 vibrational modes, and I might need 4 vibrational quantum numbers to characterize the vibrations. We're going to keep it simple. This is a diatomic. You only need one quantum number. So here's this picture. So now we just look at the oscillating dipole in the direction of the axis. The axis of the molecule is called the axis, the A-axis, or the unique axis. So imagine it's frozen in space and it's just oscillating. It's actually moving through space, but we don't care. This is the fact that it shows that it's, on average, they're pointed in all directions. But the electric field comes in, senses this, and the molecule can respond. Now, this happens at a very specific frequency. This is a very specific frequency. In the absence of any collision, it just sits there and vibrates at a very specific frequency. And that is the frequency of the center of the band. So it just sits there and vibrates at a given frequency because we relate this to the strength of this spring and the reduced mass. And so there's a relationship that we'll get to in a while that explains this frequency. It'll just sit there and vibrate forever unless it has some sort of a collision that changes that. When it does change, it has to change to another specific frequency if it's vibrating. Now the interesting thing is there's something called the zero-point energy. Even when it has V equals 0, it still oscillates with what's called half power. So even at absolute 0, a molecule, I don't know about absolute 0, but close to absolute 0. It actually is still oscillating a little bit. That's a peculiarity of a molecule. So there's infrared active and infrared inactive, and some examples again would be the symmetric stretch of CO2. So CO2 would be going like this, but if it's symmetric, you can't see it. If it's on the other hand asymmetric, you can see it. So we start talking about the types of the stretching motions. You'll get introduced to that tomorrow. So that's the light-matter interaction. Now, if we talk about electrons, you have to imagine these electrons are swarming around. This is just a cartoon, but imagine that you're familiar with the atom and the quantum numbers, perhaps, for the electronic energy levels of the atom. So basically, as the electrons go further and further out, they have different amounts of energy. That's the idea. So if the electron distribution changes from one allowed value to another, that's the electronic transition. Now when we do that, we have to move to another potential energy well because the distribution of charges is different and therefore the potential well is different. And if we move out, generally the minimum of that next well up will be up here somewhere, it'll be higher. So that difference between wells, which we'll talk about later, is associated with the change. This is just an overview cartoon which is in the notes, which helps you understand the different spectral regions and notation. So you might think about joules per mole or frequency in hertz or wavelength or wave number. They're all related. Interestingly enough, so we talked about the microwave where the rotations are, the infrared for the vibrations are, the visible and the ultraviolet where our eyes work, down to the X-ray and so on. So this is just a chart that you have in your notes. Okay. So the energy levels are discrete. Therefore, the allowed transitions result in discrete wavelengths, except for their shape. In general, we think that the rotational transitions are smaller in energy than the vibrations in the electronics. So the wavelength regions in which you see these effects. So the electronic spectra tends to be usually in the visible or UV or vacuum UV. The infrared vibrational transitions are kind of from maybe 1 micron out to, depends on the vibration, maybe out to 10 or 11 microns. And the rotations are out in the microwave region of millimeter waves. So we're going to start with rotation, then we'll go to vibration. We're going to start with the very simplest model, which is so-called rigid rotor. The equivalent entry-level model for vibration is called the simple harmonic oscillator, sometimes written as HSO. The next level up is called the non-rigid rotor or the anharmonic oscillator, and that's as far as we would go. So we'll keep the molecule simple today, diatomic. We'll start with rigid rotor and harmonic oscillator, and then eventually we'll relax that a little bit. Okay, let's see. All right, now, so we're going to do a rigid rotor. And this is like an example of how far we can go with just classical mechanics and 1 or 2 rules from quantum mechanics. So you imagine that we have one mass that's heavier than the other. So these are the masses of the nuclei connected by a massless, rigid rod of fixed length, the length being R1 plus R2. In a mechanics problem, the first thing you do when you're worried about rotation is you find the center of mass. The center of mass is somewhere along this line. It's found when R1M1 is equal to R2M2. So there's the center of mass. You find the center of mass, and then you ask about the rotation about the axes. There are 3 axes. The first one is the unique axis. It's the one through the 2 nuclei. We call that usually the A axis. Then you draw a perpendicular axis because you want 3 orthogonal axes. You pick B, that's called B. Next one is C. So right angle between B and C, but there's no preferential angle around this A axis, so you can kind of draw B wherever you want. So we're worried about the rotation about the 3 axes, A, B, and C. We won't talk much about the rotation about the A axis because the moment of inertia around that axis is so small that the spacing of the quantum states is so large that we basically are just in one state. But it actually rotates about the A axis as well. But right now we're concerned about the axis, rotation about the axis B, which would be equal to the degenerate with the rotation about the axis C. So you assume point masses, these distances, the diameter of the nucleus is a real small number, the spacing is a small number. I think it might be, that's about right, I suppose, small number. And anyway, the idea is that because this is a constant and it's massless, we immediately can introduce the moment of inertia. So what does classical mechanics tell us? Moment of inertia about the center of mass is the summation of the MI/RI squared, which can be written as mu RE squared if you insert this definition of the reduced mass. So if you define mu as M1, M2 over the sum, this moment of inertia about the B axis is mu RE squared. That's called converting a 2-body problem to a 1-body problem. There's now just one body, the reduced mass. Now, what does quantum mechanics tell us? We have to bring this in now. Quantum mechanics says that it's the angular momentum that's quantized. What's the angular momentum? Well, it would be the moment of inertia times the angular velocity, I omega. So we just go over to quantum mechanics and say, okay, tell us the rules. The rule is that I omega is the square root of jj plus 1 h bar. H bar is the Planck's constant divided by 2 pi. It also tells us that for this molecule, the allowed values of j are 0, 1, 2, 3, 4, 5. Therefore, so the angular momentum is quantized. But that also means that the energy is quantized, because if we write the rotational energy as 1/2 I omega squared, do the math, you end up with this expression right here, that the rotational energy only has discrete values set by the values of j. Minimum value of j is 0, so the minimum rotational energy is 0. All of these things are constants, h squared over 8 pi squared I. I is unique to the molecule. Every molecule has a different value of this quantity. Now we want to rotate this, convert this to what's called conventional form. So the convention for rotation is to take this rotational energy and convert it to wave number units. Wave number units. So instead of this being ergs or joules, convert this to wave number units. This divided by hc. So this is the rotational energy in wave number units. And at this point, this quantity, h over 8 pi squared ic, is called b. I should have added that onto my notes. So b is the rotational constant for that molecule. It is h over 8 pi squared ic. So if I measure the spectrum, I'm going to get b, from which I can get I. And if I know the masses, I therefore know the reduced masses, I can get the internuclear spacing. Now if I invoke, and then we've got here Planck's law again, E equals h nu, hc nu bar. So basically, these are just different ways of thinking about the energy. But in rotational energy, the convention is to call it F. Rotational energy is capital F. In units of wave numbers is this expression, and it's a function only of j, therefore. For given species, given molecule, F is a function of j. Tell me j, I can tell you F. These are the allowed rotational energy states of this diatomic molecule. Well, you should at least see Schrodinger's equation, which is the wave equation, from which all of this stuff can be derived. use the dipole moment, the probability. Now, you can use Schrodinger's equation to establish the allowed energy levels of this diatomic molecule. Now, if you want to know what transitions are allowed, that is, where can one quantum state go to another, an allowed transition. Now you have to evaluate what's called the transition probability, which involves this more complicated integral in terms of the dipole moment. We don't have to do that, but from this, you get a very simple rule. Delta J plus or minus 1. Therefore, even though this molecule may have many rotational states, any given J is only allowed to go to its neighbor. It either emits or absorbs. It can only change by 1. This is a feature, a desirable feature, of the fact that it's a rigid rotor. If you allow it to be slightly non-rigid, now you allow the slight possibility of delta J of 2, delta J of 3. In the limit that it's a rigid rotor, this is it. You can only go one place, up or down, 1. Now, I like the definition. I like this definition for rules. I say that delta J, sometimes you'll see it as delta J plus or minus 1, meaning that J can either go up or down. But if you define it another way, this is the way I like. If delta J is the difference between the upper and the lower, then it's always only plus 1. J may go up or down, but the upper one is always 1 higher than the lower one. So I like to write delta J as plus 1. But you'll see it both ways. This is a reminder. The prime denotes the upper state. The double prime always denotes the lower state. Now, since F is this quantity here, I can take the difference in wave number units, which is energy. I can take the difference between the lower state and the upper state. So if I'm in J equals 0 and I go to J equals 1, so the arrow says I'm going from J equals 0 to J equals 1. I can take the difference between the energy in 1 and 0, and I get a number of 2B. So whatever B is, that energy difference, which will be reflected in the absorption spectrum, because I'm going from 0 to 1, is at a frequency of 2B. B might have a value of, say, 2 wave numbers, which would mean that the spacing is 4 wave numbers. Let's go back to 2. Spacing of 2 wave numbers, 2 wave numbers, that's 1 over lambda. So it has physical meaning that, frequency being 1 over lambda. So 1 over 2 wave numbers and the wavelength is, I guess it's 2 centimeters. So this is a nice plot. I like this. So if we have this equation and I take these differences, that's 2B. So here's for a given value of J, this is F. J of 1 is 2B, J of 2 is 6B, J of 3 is 12B, so on. I can take what's called the first difference. So here's my F of 0, 1, 2, 3. There's an absorption line here, an absorption line here, and there's an absorption line here. There are 3 different places. The absorption from 1 to 2 is at twice the frequency of 0 to 1. So that's the first difference. The wavelengths or wave numbers of the absorption lines are the differences between the energies. That's called the first difference. You have an absorption line at 2B, 4B, 6B, 8B. The second difference is when I take this difference here, and it is always 2B, which means that in absorption spectrum, I'm going to see a line every 2B. And if I look and I see those lines and they're equally spaced, I've just determined 2B. I've identified the molecule. So that's unique to the rigid rotor. If you allow it to be slightly non-rigid, the spacings won't be exactly 2B, and the second difference won't be exactly 2B. You can look and you can see how fast is this deviating from a constant value. You can see how non-rigid it is. But in general, for a rigid rotor, we have this very simple expression. You tell me J prime, and I can tell you what, it can only go to J double prime plus, you tell me J double prime, you can only go to J prime equal to J double prime plus 1, and I can tell you the frequency or wave number at which it will absorb. I'm remembering I'm supposed to look this way a little more often. Okay, so this is a very nice simple expression. the frequency in wave number units is just 2b j double prime plus 1. So if I look at a line and I know B, I can identify J, or if I know J, I can identify B. So you measure the spectrum and you can get back the numbers you want, or if you already know the numbers, you can predict the spectrum. So this is what you would see. So if I did a transmission spectrum, the transmission would vary between 0 and 1. I'd see lines like this. And if I take that frequency and divide by 2b, since that's a constant, these are equal to j double prime plus 1. What's the minimum value of j double prime? 0. So the first line would appear here at 1. So that's the line from j equals 0 to 1, 1 to 2, 2 to 3, so on. Now it looks like they're all equally spaced, as they should be, is the corresponding j. They're equally spaced. That means I got my rigid rotor. Now, if this wavelength would be, what did I say? I took a case here of about 2.5 mil. Usually they're millimeter waves. That would correspond to a frequency of about 100 gigahertz. So the fact that it's uniform in spacing means it's very easy to identify. If maybe you had a mixture of two diatomic gases, maybe there would be some blending. But if you just have one gas, you'll immediately see this equal spacing. Now, but look at how the strength of these lines is very. This is this down here would be the absorbance, or approximately 1 minus T. Why is this one stronger than this one? They're not all equal in strength. Do we have the same number of molecules in J of 3 as we have in 0? Statistical mechanics, a rotational distribution function. So roughly speaking, this is the rotational distribution function. There's more molecules in 3 than there are in 7. This peak should follow the Boltzmann distribution. So you're beginning to see we got line positions, we got line strengths. The line strengths are kind of related to the fractional populations. That depends upon the Boltzmann distribution. Now, this is only for heteronuclear molecules. Otherwise, we wouldn't have this oscillating electric dipole moment. So if we think about the value of this rotation, so the microwave, the scientists who did this, the microwave people tend to be different than the infrared people, who are different than the UV people, because the apparatus and the notation, everything is quite different. But the microwave people would study the spectra, and they learn about the shape of you learn about the shape of the molecule. You would look at the spectrum, and you would, let's say you know that it's CO, you know the mass of carbon, the mass of oxygen. You can immediately determine the bond length accurately. Maybe if you look at the change in the spacing, you could then identify the first non-rigid term. You learn a lot about the molecule from the spectroscopy and vice versa. That shouldn't have been there. Okay, so if you measure the line spacing, which determines B, that determines I, which determines, if you know mu, that determines RE very accurately. So for one example, I think we even do this in my lab class. You measure the spacing and you find out that B has got maybe 5 or 6 significant figures. You've just measured the spacing to like an incredible length, like 10 to the minus 16th meters. So it's pretty powerful method. Okay, so the intensity, this is my simple rule. I've never seen this written anywhere. Because it's not really very accurate, but it's a good way to think. If you follow what I call the principle of equal probability, all it says is the absorption or the emission is independent of J. So in that limit, it's exactly the Boltzmann distribution. Turns out this is not exactly right, but it's so close. It's a good way to think about it. That's why absorption and emission spectra look like they do. And the same thing applies when we go to vibrations again. So here's our Boltzmann distribution again. Fractional population in J is 2J plus 1 e to the minus. Where did that 2J plus 1 come from?
Degeneracy.
What? Degeneracy. Why is it 2J plus 1? That's a trickier question. No, that's a vibrational current. So in the absence of an applied field, magnetic or electric, in the absence of a field, the molecule does not know how to orient itself. But in the presence of a field, it turns out that the angular momentum only has 2j plus 1 possible orientations. So since we don't have a field, we don't see that, but it's there. So that's the residual degeneracy that we can't get rid of unless we apply a field. Remember, it's the number of states that have the same energy. You can't distinguish these things because we don't have a field. So if you had a field, and there's some names for the effects that the physicists studied to decipher all this stuff. And they would apply different magnetic fields and electric fields. But anyway, we can't resolve this, so we just have to assign the residual degeneracy of 2j plus 1. That's where it comes from. So here's the fractional population. Now for EJ, we insert this. Okay, now I've defined a theta here, and maybe I haven't told you. Theta is hc over k times b. B has got units of wave numbers. For CO, it's about 2. What's hc over k? The students have to memorize hc over k. It's 1.44. That's the conversion between wave numbers and degrees. So hc over k. So if this B is 2 wave numbers, the characteristic temperature of rotation is 2 times 1.44, 2.88 degrees. That's the characteristic temperature associated with the spacing, with the value of B. So that's what theta is. Theta R is the rotational temperature. That's not the distribution temperature, it's the characteristic temperature associated with rotational constant B. Okay, here, this is the quantum mechanical thing that we don't have to deal with. It's just there. Okay, and the partition function for this rigid rotor is given by this. So it's just T over theta R. So we learned it at Stanford. It's T over theta R. So if temperature is 288 degrees and this is 2.8, this ratio is 100. So the Q is a sum over states. It's kind of like the total number of ways you can arrange something. It's a number that grows with temperature. And when this number is big enough, that's why we have a discrete result. Strictly speaking, this should have been an integral. But the integral can be replaced by a summation that leads to this number because theta R is so much less than T. When T gets low and gets close to theta R, you have to revisit this a little bit. What's this term here? That's the symmetry factor. So it turns out that if you have a home nuclear molecule, you can't distinguish one end or the other. You have to bring in this factor of 2. It's a little more complicated than that, actually. It brings into something called nuclear statistics, nuclear spin statistics that we're not going to get into. But right now, you should be aware of the fact when the molecule is symmetric, you may pick up a factor here. So if it's everything is easier when it's heteronuclear. Heteronuclear, it's got an absorption spectrum in the microwave. It's got an absorption spectrum in the IR. It's easy to deal with. When it's homonuclear, you have to introduce something called nuclear spin statistics. That's a little bit more than we're going to bite off today. It's a modification of statistical mechanics. Right now, we're just thinking about it as a number of ways to rotate to make it look the same, and that's good enough for now. So for CO, this would be a 1, but for nitrogen, it would be a 2. And here's my definition of this. So this hc over k is 1.44 kelvins per wave number. So my simple argument here, here's some numbers. Here's some numbers for some species that you might care about. So here's, N2 and CO are about the same. They're around 2.9, which means B is around 1.45 or so. But you'll notice then that there's some difference between O2 and N2. NO's in between, naturally. So what does that mean? Theta is smaller. Theta is smaller. So is the internuclear spacing of O2 or N2 smaller? Think about that. This one is quite different. So remember, what is theta? It's 1.44 times B. B is h over 8 pi squared I, C. So B and I are inverse. Bigger value of theta means bigger value of B, which just means smaller value of I, which means smaller length. Chlorine, that's interesting. Look at that one. So some of these molecules, these diatomic molecules, are quite different. What's the implication? If theta is small, B is small, that means the lines are closely spaced. If you go to hydrogen, molecular hydrogen, B is a big number. Boy, these lines are way apart. And if they're way apart, that means only a small number of rotational states will be excited, because it takes a lot of energy to get to the high J. So when the molecule has a small value of theta, then a lot of quantum states will be populated and the spectrum gets a little denser. You go to hydrogen, spacings are bigger, smaller number of states are populated, and the space, it's easier to look at the spectrum. Okay, you could ask, since we're now saying that the absorption spectrum or the emission spectrum looks like, well, the absorption spectrum would look like the population in the lower state. The emission spectrum would look like the population in the upper state. Did I say that right? Boltzmann distribution for that J. Different J's, they're separated by one. Now you can take the derivative and then ask, where's the peak? Where's the peak fraction? So you can solve for that, and that's kind of a classical problem that you give to students, is find the rotational state with the largest population. You could go like T over 2 theta, so it goes like the square root of T. If you increase T by a factor of 4, you'll increase the peak value of J by 2. So you might go from J of 4 to J of 8. You go up in temperature, the value of J that has the biggest population keeps moving up. What if we substitute, do isotopic substitution? So B is H over 8 pi squared IC. Now here's kind of a key point here. The internuclear spacing is set by electrical charges. I change the mass of one of the nuclei. I don't change that. I changed the mass, I changed mu, but I haven't changed R, internuclear spacing. So you can learn from this. So you can look at the ratio of the B's between, say, carbon-12 oxygen and carbon-13 oxygen, and they have this ratio. So remember, carbon-12 is, we define it to be 12. So you could look at the spacing of C12O16, and then look at the spacing of the carbon-13, and you'd find that they have different spacings. So maybe you didn't know what the mass was. You didn't know it was carbon-13, but you know you started with carbon-12. Do the experiment, look at the difference in the absorption line spacings, and you could say, that's carbon-13. And if you're clever, you could then say, and I know how much carbon-13 I have, it'd be like 1.1%. So all of this by just looking at the positions of the lines now. We're not looking at the strengths, we're just looking at the positions. Now you can say, what about this rigid rotor business? I mean, is that fair? This isn't really a rigid rotor. Why not? If this thing starts spinning faster and faster, there's something called centrifugal force pushing this out there. So you have to worry about this a little bit. So when you go up to high J, it's spinning like crazy. You're stretching the bond a little bit. The RE is going to get a little bigger. Therefore, it must actually eventually depend upon J. A bigger problem is that if it's vibrating, I don't really have just one value of R. I get some sort of range of R's, and that's a problem. So these effects basically all kind of go in the same direction. If you have centrifugal distortion, when you go up in J, the internuclear spacing goes up, which means that B goes down, which means that the spacing of the line goes down. So the centrifugal effects cause the spacing to be a little bit less when you go up in J or in V. So usually what happens is that we rewrite this expression now. Instead of saying f of J, we write f sub V. Now here's another case. This should have been a V. These subscripts should be V's, not nus. V is quantum number, nu is frequency. So this just says that it's not enough to specify J, you've also got to give me V. So now B becomes a function of V, slight function of V. And D is the distortion term, also a slight function of V. This would then be the corrected term. In the limit of no centrifugal distortion, this one goes away. In the limit of no vibrational effect, this term becomes a constant. So if you look at this and you look at it in the notes, you can show with some typical values that D is really a small number. It tends to be like 10 to the minus 6th of B. But on the other hand, this one is cubed, so you got to be careful. If J gets really big, when does J get big? High temperatures. If I go from, say, room temperature to combustion, I better be careful. If I go from combustion to a plasma, 10,000 degrees, I better be real careful. Because there can be some high J's running around, and that J cubed might come into play. So that's the correction term that you have to worry about at high J. But anyway, D is small. And now this is an interesting one. You can show that this D over B is kind of related to B over omega. Omega is going to turn out to be the vibrational frequency. So you can kind of look at the ratio of this and decide how big of a problem this is. So D over B, this is B is over omega. So this is high frequency. So when you have high frequency bonds, which means a stiff bond, this becomes less an effect. So there's some rules of thumb here. Okay, D is small, yes. Smaller for high frequency bonds, yes. Now what about this V dependence? Okay, then that should be a V, 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 V. So B sub V is written as usually the sum of two terms. A constant term, B sub E, and what do you think the E stands for? Bottom of the well is always E. RE, BE. Bottom of the well, internuclear spacing, that's B. That's the H over I pi squared, H over 8 pi squared IC, where I is the value of mu RE squared. So that's a constant for that molecule. This is the correction term that goes up with V, and alpha is a positive corrector. You hardly ever get into this one. So this is how you correct for the non-rigid rotation with these correction terms. But you want to start by thinking rigid rotor because it makes your life so simple thinking about it. Okay, the Bible is the set of volumes by Hertzberg, Canadian Nobel laureate, 1950-ish. He's the Bible, but there's one on, he's got 3 books. This is volume 1. Remember, E is the equilibrium internuclear spacing, RE. We'll look at NO as an example. Here's the value of B. Here's the value of alpha. That's over here, see? This is the correction term right here. Alpha is about 1%, about 1%. So this alpha is like a 1% correction term, but it goes up with V. That just says that the spacing for transitions in V equal 1 are different than the spacings in V equal 0 or V equal 2, and so on. We'll come to this a little bit later. Okay, so what have I done? Let's actually go to 415. Okay, now we want to combine vibration. We did rotation. We spent time on rotation because in vibration rotation, you just throw in, the rotation is already there. We just kind of add on to this now. So we start with the simple harmonic oscillator and we go to anharmonic oscillator. We'll look at the simple model, which is that gives us 2 branches instead of 3. And we'll look at the absorption spectrum, which looks like this. And we'll finally end up with some examples here. Okay, simple harmonic oscillator. Same idea. Classical model, imposed quantum rule. Works real well. Okay, so now you have to imagine a molecule that has a massless spring resting on a frictionless plane. You pull it apart, you let go, it goes forever. It's perfect. You pull it apart, let go, it'll always go back to the same place. It'll oscillate. And what do you know about a harmonic oscillator? Harmonic oscillator, maybe I should turn it around. We characterize the harmonic oscillator with a linear force law known as Hooke's force law, spring constant. It says that the restoring force is F is equal to minus K distortion, or delta x. If that's the forcing function, it will oscillate at a single frequency independent of how far you pull it apart. Linear force law, harmonic oscillator. Nonlinear spring, non-harmonic oscillator. So the virtue of these simple models is that it simplifies the math so that you can understand it. They're not exact, they're models. But the models are so easy to understand that you want to use them when you can. So we start with classical mechanics, and the spring will just oscillate away. RE is the equilibrium position again. So if it sits there and it's in its lowest vibrational level, it'll just be oscillating a little bit about RE. So you take the linear force law known as Hooke's law, which says the restoring force is the constant times the deviation from the equilibrium position. That leads to a single frequency, nu vibe, goes 1 over 2 pi k over mu. Now, unfortunately, we use k for a lot of things. Heat transfer coefficient, rate coefficient, Boltzmann's constant, spring constant. You have to be careful. They all have different units. So the fundamental frequency is the frequency at which this harmonic oscillator will vibrate, independent of the amount that you pull it apart, is given by the simple relationship in terms of the spring constant and mu. So mu is fixed. If you tell me it's CO, mu is fixed. Only variable is k. If I measure the vibrational frequencies from my spectra, I've just determined k. It's kind of a mechanical number, but it applies. The other thing you know about a harmonic oscillator, or anything with the linear force law, is that the potential energy stored in the spring is parabolic. U is 1/2 k delta r squared. So linear force law, simple model, not exactly right. It's probably best when it's small distortions. Linear force law gives us a fundamental frequency that's a constant and a parabolic expression. They're models. So this is a parabolic form. And this because the ones I've been showing you are not exactly parabolic, but they are parabolic at the bottom. So they're models. And with this expression now, we have the envelope here. At some level, you'd reach the dissociation energy. And that would then, it would go up here and it would go out, and it would be called the truncated harmonic oscillator. That's the reality. The red one is kind of like what it really is. On the repulsion side, it's always steeper. So if you want to express this potential energy, there are improvements over the parabolic form. It's harder on the left-hand side, repulsive side, and it's softer on the attraction side. But on the bottom, it's pretty parabolic. Okay, quantum mechanics. We just bring in a rule here. Quantum mechanics says that you can only have quantized values of energy, and the quantum numbers are 0, 1, 2, 3. And now we use G. So we use F for rotation, G for vibration. So should this be a nu or a V here? What's V? Only one thing, vibrational quantum number. What's nu? Only one thing, frequency. This is G of the vibrational quantum number. This should have been a V. Sorry, I made a lot of mistakes here. So this just says that the vibrational energy is the harmonic oscillator fundamental frequency times V plus 1/2. I have to convert this to wave number units. We always do this in wave number units. So we have to divide by, in this case, we divide the frequency by C. So that says the minimum value of V is 0. So this is the V equals 0, the half point, so-called 0 point or half point energy right there. V equals 1, 2, 3, 4. Now we get two things from quantum mechanics: the allowed energy levels and the allowed transitions. The allowed transition is delta V, not nu again. V upper minus V lower is 1. So it doesn't make any difference whether it's absorption or emission. V upper is 1 more than V lower. Fantastic. Rigid rotor, delta J is 1. Harmonic oscillator, delta V is 1. All of a sudden, all these other possibilities are out the door. What happens when you let this be slightly anharmonic? Now you start losing ground. So you'll have to, then what happens is this delta V says it's mostly 1, but sometimes it's 2. Sometimes it's 3. So that's the problem. So it'll be there, but you don't want to have to think about it unless you have to. So there's the real potential energy well, Okay, this is the harmonic oscillator expression. Again, that's V. And now the correction term is this one right here. It's a square term. Higher order terms. So if you get high enough up, remember now, even when V is 0, there's a very slight correction, but only this goes up with the square. So that's the anharmonic oscillator expression, which tends to decrease the energy. So it kind of shifts to the right here, it gets steeper, and the levels are not quite as high. Okay, now delta V. Whenever V changes by 1, now is this emission or absorption? Both. Remember, delta V is V upper minus V lower. It doesn't make any, the distance is the same. When V changes by 1, it's called the fundamental band. That means 0 to 1, 1 to 2, 2 to 3, 9 to 10. They're all called the fundamental. When V changes by 2, it's called the first overtone. When V changes by 3, it's called the second overtone. That's the notation. If you have CO, when you go from here to here, they're 100 times weaker. You go from here to here, it's 100 times weaker. So but in CO, they do exist. They're just really, really wimpy. Nu bar, this would be the transition energy between 0 and 1. It's the difference between G and 1 and G and 0. Remember, G is the energy. G is the energy in 1. Now this is the rotationless energy, just the vibrational energy. For 0 to 1, here's my correction term. So if X is 0, it's a harmonic oscillator. If X is not 0, there's my correction term. Omega E hasn't changed, and so on. It's in the notes. Okay, so there's a slight breakdown in the selection rules, not much. Okay, what about the partition functions? Why do we care? Partition functions are going to give us the populations. Remember, we got line positions, line strengths, line shapes. Line positions, we now almost got it under control. Line strengths, simplest rule, follows the Boltzmann distribution. It's not right, but it's not bad. So we got to get back to the partition function and the Boltzmann distribution. So here's the, oops, what did I do? I went off. Let's try and know what happens here. Okay. Vibrational partition function. So now, the partition function depends upon where you set your energy. It's like a map. The elevation, they may choose to do it above sea level, but it doesn't have to be. It's all relative. And partition functions that way too. So if you have to pick a 0 of energy. If you pick, and you can pick, there's two choices. You can pick the bottom of the potential energy well, or you can pick the level of V equals 0. And the people who do rigid rotor harmonic oscillator frequently pick as 0 the energy of the lowest state, which is different than the bottom of the well. So you have to be real careful about that. This tells me that they picked the bottom of the well. So you have to use the same expression when you do the Boltzmann fraction. You've got to use the same expression for the energy in the numerator as the denominator. That's the problem. I had a student once who spent 6 months only to find out this problem. Okay, so there's the partition function. Okay, that's my note to you right there, vibrational temperature. Here's the Boltzmann distribution right here. What's the degeneracy for vibration? It's 1, because we don't have this 2J plus 1 problem of the field that's missing. So it's just 1. So here's the Boltzmann distribution. That's, again, that should be V. Almost all the time it's supposed to be a V instead of a nu. Sorry about that. Here's our characteristic temperature. What's the value of HC over K? 1.44. And you'll use that over and over again, because a lot of the energy, energy levels are set in wave numbers, but you frequently care about temperature. Okay, so there's the characteristic temperature for vibration. Here's the characteristic numbers here for O2, N2, NO, Cl2. Remember, we had that really low value of rotational energy? Look at the big variation between oxygen and nitrogen here. Spacing of the oxygen lines is narrower than the spacing of the nitrogen. NO tends to always be in between. Now there's some typical values that you can study if you're interested. You know, this is the internuclear spacing, tends to be in angstroms. Look how much fatter and sloppier this bromine molecule is. It's got twice. Kind of a usually what you'll find is the frequency of this vibration for bromine is really small and it's really floppy. It's really kind of a big, loose, floppy molecule. That also means it has a low dissociation energy. So if it's got a low dissociation energy, big internuclear spacing, weak spring. Now look at, say, hydrogen. Big, in fact, I was going to look at this the other day. I was noticing that this number is almost exactly half of this one. I think this gives me an idea for the diagnostic that I came up with when we were in Washington together, Professor Zhu. So this is the contrast that you get with the diatomic molecules. Now these are both homonuclear and heteronuclear, but so remember, these don't have any infrared spectra. But if I put CO in, I might be able to track hydrogen because it would be resonant. So there's a lot of resonant transfer effects. I won't get into that right now. I got distracted because I saw Professor Zhu. Okay, so some diatomic molecules, calories, wave numbers, EV, force, stuff like that. Now, so we've got carbon monoxide, has a dissociation energy of about 10 electron volts. How many vibrational levels does it have? 5? 50? 500? We could at least ask this question if we had a harmonic oscillator. We don't really have a harmonic oscillator, but if we took this number, and I guess this is a better number, 256 kilocalories, you get a number of about 41. So if it were a harmonic oscillator, there would be 41 vibrational levels that it would have to climb by Boltzmann statistics before it could kind of dissociate. Because the spacing gets narrower and narrower as I go up, because of the anharmonic effects, there are more than 41. We're going to have an example of this in the next couple of days. I know it's a bigger number. Okay. There's a lot of interesting approximations. There's something called the Born-Oppenheimer approximation. So you got this thing vibrating and rotating. We've argued that these energies are independent. That's sometimes called the Born-Oppenheimer approximation. So we just think of these energies as independent. Why? Makes everything so much simpler. Strictly speaking, it's not right. If you have a higher level of vibration and some rotation, you're going to have a different energy than given by the independence rule. We have these simple selection rules, delta V of 1, delta J. Okay, I violated my own rule here. Oh, okay, good thing. All right. For vibration rotation, delta V is plus 1. V upper minus V lower, always 1. But what about J? If it's pure rotation, J upper and J lower always differ by 1. But when I start from here, Vj, and I go down here to V, now J has two choices. And I get two branches. They're called P and R. And sometimes the rule is that you can have delta J of plus 1, 0, or minus 1. And then you have 3 branches. When there's only 2, it's P and R. If there's 3, it's P, Q, and R. Yeah, so the selection rule changes now. You always go down in energy for emission, but J can go up or down 1 unit. Line positions. Okay, now when we talk about summed energy of F plus G, we now take the sum and we give it a letter T. So T is the symbol that's usually used for the term energy, the total energy. It would be F plus G. And the frequency of the transition is the difference just between, is conservation of energy, upper minus lower. Okay, so because there's 2 possibilities, you get 2 answers. Delta J, which by definition now is J prime minus J double prime, can be either one, plus or minus. And so now when I finally plot the absorption spectrum, I see an R branch, there's a center. That's called the null gap. That's the rotationless transition wave number. Then you get a different wavelength for a given value, for each value of J. You get a different line. So here we are. We have a V equals 0 and a given J. V double prime 0, J double prime. You can go here or you can go here. Two solutions. This one is shorter than this one. So usually these units are in energy to the right. The R is always bigger. R is always delta J of R is delta J plus 1. So the R branch is always on the high energy side of the null gap. Always. And you can identify each of these lines. What's the minimum value of J here? 0. Ah, but what about this? What if this is 0? I'm not allowed to go to -1, J of -1. So that one doesn't, you can't have that one. You have to be careful. Minimum value of J is 0. So when you look down here, you'll see the first line on the R branch is R of 0, but the first one in the P branch is P of 1. The first one you can get to end up at 0 here is a 1. That's this little subtlety. That's why there's no line right there. That's called the null gap. Here's the notation. OPQRS is the alphabet soup. So this is for the delta J. We're dealing here with -1 and +1, so we have P and R. There are some cases where you can have Q, and even some cases where you can have O and S, but we won't deal with that today. Simple model. I think I'm running over. Okay. I went from being too short to being too long. Okay. There's notation for these lines in the R branch. It's always the difference in G's plus the difference in the F's. And you can find an expression for the R, and you can find an expression for the P. And you can talk about the differences between the two peaks. Here's our branch. Here's our picture again. So again, if you buy into my simple model that these just reflected Boltzmann distributions, then these are just the Boltzmann distributions. Except you'll notice the R is always a little taller than the P, and that's one of the problems. Okay, let's see. I think I'm almost done. I've got some improved model that's in the notes. Let me skip through there. That's the B sub B. See what I've got here. Okay. Just like you can look at the infrared spectrum when it's a rigid rotor and extract immediately a value of B, you can look, if you look at enough lines, you can also solve for this correction term alpha. And that's done. I think I'm going to show, yeah. That's called the four-track parabola. So here's the spectrum. And now if you plot those lines versus the distance from the null gap, you'll see the R branch goes up and then it peels back. And the P branch goes out. And it does that because alpha is finite. If alpha were 0, they'd be on straight lines. So you can measure the line positions and infer alpha. And the plot on which this is done is called the four-track parabola. Now, when you calculate where this happens, dRj, dj, you can solve for this, and it's approximately B over alpha. How big was B over alpha when the example I showed you earlier? 100. So that means that it happens at high J. You're not going to see it unless you heat this thing up to pretty high temperatures. You won't see it. But it's there. So it's just usually not observed. But we do see this in like my lab course. We see this deviation. We measure the alphas pretty accurately. Okay, so I just want to show you how we kind of do this. So we do this in the lab. These are the 4 parameters in the spectrum. B, alpha, omega, and X. That's the harmonic correction. That's the distortion for vibration. There's 2 approaches. You measure the spectrum, just fit it. But there's a couple of other approaches. I'm going to show you one example here. Okay, and it's called the method. I don't know how common this is. This is called the method of common upper state. So you find in your spectrum the 2 lines that end up in the same place, and the difference of these lines is the frequency, and the difference between those immediately solves for B double prime. So common upper state, you can solve for B in the lower state. Common lower state, you can solve for the B in the upper state. Method of common states. This is now, we're now moving into stuff that's a little more sophisticated. Yeah, question?
How do you know you have a common upper state? You just
well, you identify the lines in the spectrum. So you'll say this is P of 10 and this is if I said P of 10 and R of 10, they started at the same, they have the same lower state. So you identify the lines and their wavelengths or frequencies. So you have all the numbers. The question is what to do with them. By looking at them, by fitting them, or by using this simple method here, you can, and we'll do this in an example. I'm going to show you in a couple days, a couple lectures. I did the isotope effects. Why do I show you this? If you do the spectrum of CO in the lab, as we do in my class, you'll see all these interlopers. What is that? The fact that you got 1.1% carbon-13 in every bottle of CO. That's the natural abundance ratio of carbon-13. So we see it. They're there. So what you do is you record the spectrum, you measure the wavelengths, identify these features, then you can use that common method of common states to get the values of B. Okay, I just got way too much. It's interesting, I went way over on this one. So you can see this pretty dramatically when you look at HCl because the relative abundances of those two species is such. Hot bands, I have one more thing. Hot bands are when you have excited states. So if you heat your sample up, the absorption takes place not only from V equals 0, but also from V equals 1. And that starts to overlap on your spectrum. And do I have an example? Yeah, I have an example. So first of all, if you looked at carbon monoxide, as you go up in temperature from 100 to 300 to 1,000, look how the distribution spreads out and you go to higher J. But look how it differs for HCl, which has this huge B value. A lot fewer lines. Okay, why do I like the infrared? A lot of the combustion gases we care about, NO, CO, CO2, water, fuel, all absorb in the infrared. It's a really good place to work to measure these combustion species. Small species have discrete spectra, even though it looks like they're overlapping here, they're all separated. Big molecules have to do a different strategy. Well, I can't believe that I put in so much stuff in this talk. I apologize. Went from too short to too long. Okay, so sometimes we make measurements behind reflected shock waves in our shock tube, and we measure species. Oh, I just want to show this one. I think this is the last slide. So this is a methylformate. This is the structure of methylformate. We shock heat it to 1400 degrees. We monitor versus time the CO in the infrared, the methanol in the infrared, the removal of methylphorate in the infrared, the methane or the CO2 in the infrared. Formaldehyde we actually measure in the UV. That's what you can do in the infrared. Line of sight absorption. I think that's the end. Yeah, next. Apologize for running over. Took you 10 minutes too long. Any questions? Okay, I guess we've only got maybe 10 minutes for a break here, and we'll resume.